Hey everybody, this is lesson 4.5, the center of mass. Center of mass is kind of a weird concept. It's pretty easy to calculate, but the importance of it is sort of hard to emphasize. There are two applications of it. I think the first would be center of mass can be used to track the way rigid objects move. So in physics, usually we're talking about a box or a point particle, a circular thing that we can think of as a point. But when it comes to very rigid objects, things with a very non-uniform shape, like a baseball bat, it's hard to figure out how that object is going to move. So by finding the center of mass of this object, we can predict how that bat is going to move. So as this bat is twirling, moving through the air, I can still track this dot to move in the parabolic shape. So that's the first application of center of mass. This one, a box and a sphere, they have a very obvious center of mass. But with a baseball bat, it would be hard to find. Maybe it would be even farther up. But basically, this is finding the center of mass of this object is quite complex. You need to use calculus, a concept that people generally learn in college or senior year of high school. So we won't be doing much of that. The more simple application of center of mass would be to take two objects and find the center of mass between them. For example, if we took the center of mass of a planet and its moon, I have a drawing here, I don't think y'all need to draw it, but if you take the center of mass of a planet and a moon, the center of mass is going to be closer to the larger of those two things. In addition, if you took the center of mass of two people on a seesaw, maybe you've got a larger child and a smaller child, the center of mass is going to be closer to the larger child. And we can see here, if you're going to balance a seesaw with a large kid and a small kid, you're going to put the fulcrum closer to that larger kid in order to balance this better. So center of mass is a point of balance, it's a point between two objects, or it is a specific point on a rigid individual object. Basically what we do in order to find center of mass of this, we would have to look at each individual atom in this baseball bat and do some calculus to calculate center of mass of every single one of those. We're going to do a simpler calculation. I'll drop in the equation right here. Okay, center of mass in our class is going to be the average location of a set of masses. The average location of a set of masses, and it is a weighted average, which means if you have two objects, one of which is very massive, the center of mass is going to be closer to that massive object. The equation for this is quite fascinating to me because it looks like the way you calculate average. If you wanted to calculate your average test scores, you would add your test scores together and divide it by the total available points. To get your center of mass, you add up your positions and you divide it by the available masses. So here's how we write it. It's actually the mass times the position. So if I have an object located at x equals 3, we would take the mass of that object times 3. We do that for every object on the line. And we divide it by the total mass. So there's our equation. Here's what we've written. XCM, position of the center of mass, equals m1x1 plus m2x2 plus however many you have, divided by m1 plus m2 plus all the other masses that might be in the system. We're generally, most of the time, going to use two objects, so we can kind of cut out the dots when that's the case. Center of mass is not always in one dimension. We can also calculate the y center of mass. So with this baseball bat here, if I had it at rest, I would have to figure out the x location there, and I would figure out the y center of mass. So we're also going to write this equation in the y form, which looks like this. Same exact thing, but instead of x's, it's y's. So if it's a one-dimensional system, if the objects exist on a line, you just find whichever one of these makes sense. Is it on a horizontal line or is it on a vertical line? You would do x and y respectively. If you have a system of objects, which we might get to in this video, I'm not so certain. If you had something like this, if you have objects that are randomly distributed through two dimensions, we would have to figure out the x center of these and the y center of these, and we'd write them in a coordinate pair, like this one is here. So sometimes if you do both of these, you write it as an ordered pair. So your answer would be, in that case, it was 2 meters, 1.7 meters, which means the center of mass is 2 meters this way and 1.7 meters that way. So you need an origin for this. You need a 0, 0 position for these. Let's get to an example of these. First of which is quite easy. The equation is quite easy to use once you've comprehended the meaning of it. So here it is. I'm just going to draw it out. We're going to calculate center of mass. And I will, instead of writing a bunch of numbers, I'm going to put these on a line. So here's our line for the problem. Okay, first, we need a position 0. And I'm going to have 10 points on this line. 10 hash marks. 1, 2, 3, 4. There's 5, 6, 7, 8, 9, and 10. In this case, I'm just going to draw the masses as circles on this line. So right here at position 6, we have a 12 kilogram mass. And back at position 2, we have a 5 kilogram mass. So I hope it's easy to see how we're going to calculate this. First of all, the x form is more appropriate because we have a horizontal line. Second of all, this is x equals 2 and x equals 6. So the 2 will go in for x1 and the 6 will go in for x2. The 5 goes in for m1 and the 12 goes in for m2. So quite an easy equation to use when it's set up simply like this. You're not always given a number line. Sometimes you have to throw the number line down yourself. This may have been written like this. Maybe it's written 5 kilograms and 12 kilograms, and they're a distance of, what would it be, 1, 2, 3, 4 meters apart. That's sometimes the setup, and we would just say that this is at position 1 instead. Don't think it would work if it's at position 0, because then you're canceling everything out. Oh, no, it would. Yeah, you could say this is at position 0 and this is at position 4. So let's just use the original form and we'll write it in. So x center of mass is going to be 5 times 2 plus 12 times 6 divided by 5 plus 12. If you're following along with a calculator, it's important to have both your numerator and your denominator in parentheses for this problem because of those addition terms, because of that addition sign. And XCM is going to be 4.82. I'm quite curious about how this one will work out. Go ahead and write that one down as well. It'll be interesting to see how it works out. So 5, 12, they're 4 meters apart. We're not given a number line, so we need to establish it ourselves. It doesn't matter what number I pick for this. If this is 15, that would be 19. If this is 20, that's 24. But zeros are good. Let's say that is 0 meters, which means that the other one would be 4 meters. Let's just verify that it works out. Let's go ahead and write this one down as well. We'll skip one of the longer examples that are coming up. So XCM equals, well, it's going to be 0. 5 times 0 plus 12 times 4 over 12 plus 5. I flipped them, but that's okay. It's addition. They will still work out. And let's verify. Let's see if this works. So really it's just 12 times 4 times 4 divided by 17. And we're going to get 2.82. And the reason these answers are different is because position is all relative. So we've established this as position 0. The center of mass is 2.82 meters to the right. And with this as position 0, it's 4.82 meters to the right, but it still falls in the same location. So what we've done for each of these two is established a different position 0. And so there's two different ways to write the same thing. The point is, I'll have to give you some sort of frame of reference for each problem so everyone gets the same answer. But basically, we can see it right here. There's center of mass. It's a little closer to the 12. And just here, same thing. Would be 1, 2, be right about there. Center of mass is closer to the 12. So position is all relative. That's a cool problem. If you're concerned about why the answers are different, don't worry about it. I'll always provide some context. That's just for fun. Let's look at the next concept. Okay. Another concept that is going to be a little more familiar than center of mass based on what we've done in previous days, and that is the velocity of center of mass. Velocity of center of mass. It is kind of like how a center of mass is the average position, the average location of the objects. Velocity of center of mass is the velocity of Oh, snap. It's the average velocity. The average velocity of a set of masses, and I'm going to put a semicolon here. The average velocity of a set of masses. Also noteworthy is that VCM, velocity center of mass, is conserved. During the collisions that we see. So if there's an external force, velocity of center of mass is not conserved. If there's no external force, velocity of center of mass is conserved. So let me read this again. The average velocity of a set of masses, semicolon, velocity center of mass, is conserved during collisions. The equation is going to mirror the last equation we've written. We're only going to write it in one dimension, however. VCM equals M1 V1 plus M2 V2 plus ... because there might be 2 objects, might be 3 objects, might be 4. And in the denominator, same thing as that first equation today. So velocity of center of mass is again a weighted average. The more massive objects, don't forget that bottom part, the more massive objects will hold greater influence on this equation because their velocities are multiplied by their masses, and the lesser mass objects will have less influence on the center of mass velocity. So the interesting thing about this is right here, the fact that the velocity of center of mass is conserved. So when you have 2 carts moving toward one another, there is an imaginary dot that is constantly moving in one direction. And as these 2 carts come to collide, when the collision occurs, this imaginary dot, this velocity of center of mass, will continue moving. It won't move at all. It won't change direction at all. It won't decelerate or accelerate upon the collision. And we'll demonstrate that here in our final example today. We're going to calculate VCM before and after the collision. So in this collision, momentum is conserved. If you feel like verifying that, you can go ahead and have a great old time with it. But we're not going to verify that. We're just going to verify the velocity of center of mass is conserved. So we've done our before picture. In a moment, I'll draw the after picture. So these 2 carts are moving toward one another. They collide, and they move in opposite directions. And here's our given information. From left to right, the first cart has a mass of 3 kilograms. I'm going to write that inside the cart. The second cart has a mass of 2 kilograms. So we can write that here as well in the after picture. So 3 kilograms and 2 kilograms. Their velocities are 9, -7, and continuing on. negative 3.8, and positive 12.2. So I'll read those. I've written quite small. Here's what they say. Before the collision, it's 9 meters per second and negative 7 meters per second. After the collision, it's negative 3.8 meters per second and positive 12.2 meters per second. So, center of mass, I hope it's easy to see how to calculate. I'll write the equation, and we can just refer to it right here. So, this will be object 1. There's velocity 1. This is object 2 with mass 2 and velocity 2. And same thing for here. There's no before and after in this equation. This equation can only be used at instantaneous moments in time. So we'll use the same equation twice, but with different numbers. So here's the first one. VCM equals 3 times 9 plus 2 times negative 7 divided by 3 plus 2. Let's write out the other one as well before using our calculator. VCM equals 3 times negative 3.8 plus 2 times 12.2 divided by 3 plus 2. So here we go. The left-hand side, it'll be, top should be in parentheses. So it'll be 3 times 9 plus 2 times negative 7. Close that parentheses, divided by 3 plus 2. So we'll get 2.6. If we get 2.6 for the other one, physics works. If we don't get 2.6 for this one, there's a problem with our universe. We should probably move to a new one. So here's our other one. Let's see if it works. 3 times negative 3.8 plus 2 times 12.2 divided by 3 plus 2. Boom goes the dynamite. We got 2.6. So this is the case for any collision as long as there's no external forces. Momentum is conserved, and so is the velocity of center of mass. We'll probably begin class with this example here. So this is the two-dimensional center of mass. I thought it was interesting. Maybe take a guess. Probably be somewhere in here. Well, actually, no, we have our answer, 1.7. So just keep in mind that center of mass is not always a one-dimensional case like this. For moving objects, you could also find a velocity of center of mass that is not one-dimensional. So picture that imaginary dot that moves sideways. It's moving to the right at a speed of 2.6 meters per second, and when they collide, it does not change. It keeps moving, still moving to the right. That's it. Thanks for watching. Post these notes on Google Classroom, please. Cheers.